Today we'll start with Antonin Guilloux from Paris. He will talk about character variety of free manifolds.
Okay, so thank you for the invitation. It's really a pleasure to be here. And so I will talk, like Stefan, of a related topic, which is character variety for three manifolds. And so I think Johan will speak of the same topic tomorrow, the day after tomorrow. So I will begin with an introduction to character variety, and then to present a joint result with Elisha Falbel about dimension of component of this variety. So let's see the general framework. I will consider some finitely generated group gamma, and it will always be either the fundamental group of a surface, which will in my talk always be closed oriented surface. In fact, it will be the torus or the genus 2 surface. So this is the first example, and the main example for my talk will be the fundamental group of a three variety. Closed with boundary and you may think classical example will be not complement. You may think hyperbolic if you want. Okay, so this is the group, the discrete group I will look at, and
The free manifold usually variety.
Yeah, okay. This is a three manifold indeed. There will be variety later on. And there will be another group, G, which will be, well, mostly it will be a special inner group. And I will in fact always take a semi-simple linear complex algebraic group. In my talk, I will always assume complex, but for some examples, but theoretically it's really much easier to assume complex. Character variety for real groups are not so well behaved, so I think that we should focus to SLN. So the problem of the character variety is to understand representations of gamma into G. So we have three kind of spaces. First of all, we have what is called the representation variety, which are just a morphism from gamma to G, and this is an defined algebraic variety. representation of the group. It gives you the number of generators, gives you plus the dimension of the group gives you the dimension of the FIX spice, and the relators give you the polynomials to consider. So this space is a space of interest for us, but as is classical in these topics, we want to consider two representations that are conjugated equivalent. So the first quotient to consider is a quotient by the conjugation. Conjugation on the space of representation. So why would I make this quotient is because we saw it yesterday with lattices up to conjugation. When you have a representation from gamma to G, you can always conjugate in G, and this is not very interesting. Okay, you can always build new representation from the beginning one by conjugating, but this is not very interesting. And from a geometric point of view, I will not go that much in that direction, but this space, I like to call it the monodromy space, because I like to see it as the space of possible monodromy of geometric structure on the variety n, the manifold n. And in this, if you think in this aspect, then monodromy is really defined up to conjugation. So this is a natural space from the geometric point of view, but this is a bad behaved space. This quotient is, well, the action of G is not free. It's not from a geometric and a algebraic co-geometric point of view. This is a bad space. This is not Hausdorff. This is not good. So you define the character variety by taking the GIT quotient. Well, I will not go much further into GIT quotient, but let's say that it is the affine algebraic variety whose algebra function is the algebra of G invariant functions on the first one, the representation variety. Okay, so you have an affine algebraic variety with the action of a group. You can look at G invariant functions. It gives you an algebra function, and you can prove that in this case it is finitely generated, and so you take the affine variety for which it is an algebra function. Okay. In this case, one may be more precise. So in this case, here I should stress that I assume G to be SNNC by work of Puccini. You can choose some elements in gamma such that character variety is indeed expressed in terms of the trace of image of this gamma I, so that is identified with the image. So you have this map from the representation variety to some affine space, mapping a representation rule to the collection of the trace of the images of the elements. Okay. So you have this map.
The closure of the image.
With what I am saying.
No.
No, at this point, no.
Okay.
No,
It's closed.
it's closed.
Yeah.
It's closed. Here I should stress out this, the image of this map. So here you have an affine algebraic variety. I'm not saying that this is C to the n. Here you have algebraic relation between those traces, and the character variety is identified with, well, this affine algebraic variety defined here. Okay, maybe I should give some examples. Three groups and two generators. So you have to choose who is gamma and who is G. So G is SL2C. Then let's say in this case the character variety is C3 with coordinates the trace of the image of A, of B, and of the product. Okay, so here there are no relation between these traces, and it, well, for this case you can prove it using the well-known trace formula for SL2, and well, there is a nice description by Goldman of this space, and the nice description of the real points of this variety in order to look at representation inside, which lies inside SU2 or SL2R. So there is a nice real geometry inside this complex variety. Okay, and maybe I should give the example of SL3. So I don't know who is responsible for this result. I should say, I think that Klein or Frick knew that. I don't know if they stated it in this way. And now for the case SL3, and still the free group into generator, there is a work of Lawton, which says that the character variety of F2 in SL3 is a double ramified cover over C to the 8, and I can be a little bit more explicit. You take the traces of A and its inverse of B and its inverse then of the four products between A, B and their inverse. So this gives you C to the 8 numbers, and then the last one, the trace of the commutator, will verify the polynomial of degree 2 in these numbers. Okay. So the ramifying locus, the locus of ramification will be the locus of vanishing of the discriminant, this relation, and you can really understand this double ramified cover. Okay. Okay, and maybe a last example, which is closer to my topic, which is character variety for 3 manifolds. So if you take the fundamental group of the 8-node complement, you can compute the character variety for SL2, and you will find 2 components. One containing the hyperbolic monodromy. What I mean is that this manifold carries a complete hyperbolic structure. So you have a monodromy for this complete hyperbolic structure, the 8-node complement. Can be seen as H3 mod some rho of its fundamental group, rho from gamma to SL2C, PSL2C, and so, okay, I'm wrong here. Sorry, here I should. It's also true, but it's also, yeah. Yes, it's also true. It's always a problem for me to decide whether I'm looking in PSL2 or SL2, and I hope I won't make mistakes. More naturally here, you would like to look into PSL2 as the isometry group of H3, but then you can look at how to lift representation. So I hope that what I say is not for the case PSL2. Never mind. So there is one component which is in fact an hyperbolic curve, an elliptic curve, which contains a hyperbolic monodromy, and another one which composed of reducible representations. So I don't know exactly what Joan Porty will talk about, but maybe he will present more precisely this example. So I will just go on. So this is a general framework of character variety. I will be narrating, and my point is to focus on the case of gamma, the fundamental group of a three manifold, and G, S, L, and C, and to give a lower bound on the dimension of components of this character variety. Okay, but for that I need some information in the case of surface groups. So I will review very briefly some facts in the surface group. Are there any questions? So the problem of representation of surface group is very much studied, and there is a very vast literature. So I will not review everything. Far from that. I will review a theorem of Vail and Goldman about dimensions that I will need later on, and it will give me a reason to introduce some definitions. Okay, so here for all this section, gamma is the fundamental group of surface, and S close oriented. So in this case, the first example to look at is at least in the case the genus of S is more than 2, you want to look at hyperbolic structure on the surface, and so an hyperbolic structure is related to a point in the character variety of gamma into PSL to R. Okay, so here you see a lot of components which are parameterized by the other class of representations, and one of them is the Teichmüller space. Up to complex conjugation maybe, but you are inside the character variety. There is a component which corresponds to the Teichmüller space, and maybe I should say that this is the beginning of the story of character varieties. Is that you are looking at the Teichmüller space as a component of the representation variety in Poincaré and Klein works. This representation variety, character variety appears in order to study hyperbolic structures and on the surface. Okay, and then this is now a classical problem to look at deformations of representation inside other groups. Okay, PSLN-R or SL2C, and then any type of option in the center. So you have I will just drop some name of what you can find inside those character variety. You can find famous things like itching components, higher attachment, which are more or less the same as attachment spaces, and so on. So, I'm not able to review all the beautiful math that you have inside these deformations. I just mention it because it is more or less a starting point for my work to look at character variety of three manifolds inside, not inside SL2C as would be natural for hyperbolic structures, but inside higher rank groups like SLNC. And the case of surface group is a great inspiration to look at what they do, how they do that, and what you can upgrade to representation of three manifolds group. The two worlds are very different, and in the case of surface group, you have you have a lot of tools, but as a beginning point, you have a very nice presentation of the fundamental group, very coherent for all genus, that lets you work, and so on. So there is a whole world of math here, but I will just, maybe sadly, I will just need for my talk here the formula by Weil and reviewed by Goldman, which computes the dimension of representation variety and character varieties for surface group. So let's state it. Game of so gamma is a fundamental group of the surface. I stress out that the torus can be put here, not higher genus, not only higher genus surfaces, and I will need the case of the torus. Then the dimension of, well, let me write it in the, so I have this affine algebraic variety, this point, I take a point inside this variety, and now I take the Zariski tangent space, this is a complex vector space, and I want to know the dimension of it, and it is 2g minus 1 times times the dimension of G plus the dimension of the centralizer of the representation. Okay, if your representation is too small, the dimension of the Zariski tangent space is bigger. And so this is for representation variety, and for character variety, more or less you just mod out by G, taking into account that if rho has a centralizer, when you mod out, the action is not free, so you have to you don't mod out that much as you would think, so you lose one dimension G because of the modding out, but you have to add one time the dimension of the centralizer, which is, well, I have to say that this formula is surprising first sight, because here it's a point of the character variety, which is related, but in a strange way to representation. And in fact, this side does not depend on the actual representation you are looking at. Okay. So there is a projection from the representation variety to the character variety, but this is not one-to-one, of course. And so here it could depend on rho, the choice of rho, but in fact it does not.
This is for every row, or is there any condition for row?
No, there are conditions on G for rho. No. Okay. And the condition of G is, well, let's say reductive complex algebraic, linear complex algebraic group is enough. And so let's have a look at this formula. For example, in the case of the torus, which will be important for us. So if gamma is a fundamental group of the torus, it's Z2, and here you have the dimension. So here the dimension at a point, the representation variety is dimension of G plus dimension of the centralizer of rho. Okay. And here the fact, well, here you have to look at the centralizer of rho, because gamma is abelian. So when you look at an image of gamma inside SL2C, there will be a centralizer. Okay. It will not be empty. It will not be trivial. So in this case, this term always appear, and in fact, in this case, the minimal dimension of the centralizer in the semisimple group is the rank of the semisimple group. So for SLN, so a generic representation of Z2 will be diagonal with distinct eigenvalues. And so the centralizer is exactly the maximal torus of diagonal matrices, and it is of dimension n-1. Another example, not generic, but example of such representation which have the minimal dimension of the centralizer. So are unipotent representation which have only one Jordan decomposition block. So these two kind of representation have minimal dimension of centralizer. Okay. Those representation will be important for me, so I give them name. Well, there is a classical name for this type of elements in semi-simple Lie groups. So definition: a representation rho from Z2 to G is regular if the centralizer has the minimal dimension. In the case of, well, this is the definition by Steinberg, and in the case of SLN, there are two possibilities. Or this is a diagonal representation. No, well, let's see. The single element is regular if either it is diagonal with semi-simple diagonal with distinct eigenvalues, or it is a unipotent element with a single Jordan block. Okay, so then this is the work of Steinberg, and there is a whole theory of regular elements in semi-simple and reductive complex algebraic groups. So I will just mention that proposition for G, which equals SLN rho, if rho is irregular. Sorry. Then it stabilize finite number of subspaces in C to the n. Okay. If you believe my description, it's almost done, because if you are diagonal with different eigenvalue, you have a finite number of stabilized subspaces, and also in the case of unipotent with a single Jordan block. But if you're not in this case, you will have more subspaces. Well, the exact, in the SLN case, you can have a mix. Well, I was not precise enough. You can have a mix of this one, of these two examples. That is, regular means for every eigenvalue there is only one Jordan block, and in this case you will have only a finite number of stabilized subspaces. Okay, so this is regular for SLN. Okay, and from Weil-Goldman theorem, we see that regular representation of Z2 are the ones which have the minimal dimension of Zariski tangent space. So those are smooth points of the character variety, okay, because they have the minimal dimension of the space. And for this point, the character variety is of dimension exactly 2 times the rank meaning that, well, we can recover that in another way. If you are looking only at generic representation, which will be diagonal with distinct eigenvalues, so you have to choose 2 representation with 2 matrices which commute, which are diagonalizable with distinct eigenvalues up to conjugacy. So you just have to choose the eigenvalues, and this is, you have the choice is 2 times the rank of the group. You have 2 times n minus 1 eigenvalues to choose. Okay. And a last point about regular representation. No. I will say that later. Okay. Okay, so this is the first more technical definition that I will need, and the other ones that more or less I already use. Is that a representation is irreducible if it does not preserve any subspace of Cn. Well, once more, there is a definition, a general definition for G, a semi-simple group, and so here. Here, this is a general gamma, and a proposition, a remark, is that if rho is irreducible, its centralizer is exactly the centralizer of the group, and so for the higher genus case, this part can vanish, and it vanishes for irreducible representation, and in this way you recover the well-known fact that irreducible representation are smooth points of the representation variety and correspond are points where the quotient is smooth and corresponds to the smooth points. Well, to smooth, the component corresponds to smooth points here. So you can recover the fact about irreducible representation for surface group with this remark. Okay. will. Okay. And I have to make a slightly stronger definition of strong irreducibility and I say that a representation is strongly irreducible if any finite how did I say? If no finite index subgroup stabilizes a subspace. Okay? So maybe I should say not virtually reducible. So I don't want to stabilize a subspace, but I do not want either to have a subspace with a finite orbit inside the subspace of Cn. Okay, you can think about anti-diagonal representation inside SL2C. So those are the two conditions on representation that I will put later on in order to have the bound for dimension. So let me go on with that. Now I will focus on gamma, the fundamental group of a three-manifold compact with non-empty boundary. And orientable. And I will assume that there are no spheres in the boundary. Okay. If there are spheres, I just put a ball. Ball inside, and this is a technical assumption, but it will be nicer with this assumption. So inside the boundary of M, there are some tori, let's say T tori, and other higher genus surfaces. And there is a result by Thurston and Culler-Shalen, which say that in this case, the character variety of gamma inside SL2C, the components of this character variety have a bounded below dimension, provided they contain some representation which is not too degenerate. So I will state a general result containing the the original one for SL2 is Thurston and then Culler-Shalen, and the generalization is a joint work with Elisha Falbel. So I take a component of the character variety of this fundamental group into SLNC or into the semi-simple linear complex algebraic group, and I look at its preimage inside the representation variety, and then I have really the same bound stated at both levels. The dimension of the component in the character variety is t times n minus 1 minus n squared minus 1 times the Euler characteristic of the manifold, and inside the representation variety, you have the same bound, just you have to add the dimension of the group once the dimension of the group, because you from there to there you mod out by the group. So this is a bound, and in the case of SL2, this is 1 and this is 3. So this is a bound from Thurston and Culler-Shalen, and maybe in more in terms of semi-simple groups, this is the rank of the group and this is the dimension of the group. Okay. So we have more or less the same number appearing than in the Goldman formula. The rank of the group coming from some centralizer and the dimension of the group. Okay. But there is a blank here because there is an hypothesis. This is false, like that. There are components that may be points, and so you have to make an assumption. You have to assume that in this component there is a representation which is not too degenerate, which is irreducible, and what I call boundary regular. I will explain what it means just now. Okay, but if you have a representation which is not too degenerated, strongly irreducible, and the boundary regular, then you have this bound. So this is striking that a single representation gives you such an information on the whole component of the character variety. And now I have to define boundary regular Well, I define regular for representation of Z2. Now gamma is the fundamental group of the 3 variety, but I have a collection of natural Z2 inside of gamma, the fundamental group of the tori. Okay, if so. I ask that for each boundary torus, the representation restricted to its fundamental group is regular. Okay, so well, here I'm a bit sloppy. The fundamental group of the torus is not included inside the fundamental group of M. In fact, there are a lot of copies that are included, but just pick one of this copy and check if it is regular or not, and if it is, all the copies will be, and if it's not, none will be, because all the copies are conjugated and regularity is invariant under conjugation. Okay, so I will pretend, more or less for all my talks, I will pretend that the fundamental group of the torus is included inside the fundamental group of the manifold, which is not exactly true. Okay. So, okay, this is the definition of boundary regular. For any Z2 that you see at the boundary, you don't want representations that are too degenerated, like you don't want identity representation when restricted to the boundary torus. And in the case of SL2, you don't want it to be central. Okay. I'm checking if I have not forgotten something. Okay, so I will present a proof of this theorem, but before I will mention that it is a theoretical theorem, but it can help to compute actual character variety. So Johan will, I think, present some techniques to compute character varieties for let's say maybe SL3C, I hope. SL3C? No, not SL2. Okay. So there are other techniques for SL3C, but in the case of SL3C, if you analyze this affine algebraic variety, you find a complicated affine algebraic variety, which may have a lot of components. And if you want to compute examples, for example, 8-knot complement, well, it's still for the 8-knot complement, it's a difficult computation in terms of affine algebraic varieties. The ideal defining the variety are huge, and you have more or less to compute covalent basis and decomposition, product decomposition, and this is not too big, but almost. And with this theorem, you can, when you compute with affine algebraic variety and you make projection and so on, in order to simplify the ideals, to eliminate variables and things like that, very often you create what is called spurious components. You create components which were not here at the beginning because you are projecting things which are maybe not exactly in generic position and so on. But so you can do computation, and at the end you have a very big variety, and some components actually correspond to actual components of the character variety, and some components are spurious. With this theorem, you can say, well, if I just search for components of the character variety containing irreducible representation and boundary regular, then I already know already know bound the dimension, so I can just throw out all the small components. And in fact, it helps a lot in computation. And I am trying with collaborators to compute the character variety for the whitehead link complement inside SL3C, and without this information, I think we will not even try to do that. Okay, so this was just a remark, and I will go on with the proof. And the proof, in fact, the proof is more or less the same than Thurston proof for this theorem in case of SL2. But for SL2, you have these trace relations, and you can you can do a lot of computation by hand. So in the original proof of Thurston and Culler-Shalen, there is a piece where you really have to look at element in SL2, the traces, whether it is identity or unipotent, and so on. And here we will bypass it by a more geometrical approach, which allows the generalization. So more or less it's the original proof and some technical points made through more geometric analysis. So those who know the original proof will not be at all surprised by what I will do. Okay, so the proof is by induction on the number of tori. Okay, which may seem surprise if it's your first look at this proof, but still it's a very nice idea how to make an induction on this number of tori. So maybe I will begin with the initialization. When t is 0, when you have manifold which is compact, which has a non-empty boundary, so there is a boundary which does not contain tori, and so n as a homotopy type, I should say, of two-dimensional CW complex with one vertex, some edges, some two sets. Okay, you can just deflate the manifold on skeleton, two skeleton.
Assume n is not closed.
Sorry, I didn't hear.
To assume n is not closed.
M as a non-empty boundary.
Okay.
Okay, and we will check in the procedures that we just create more boundary, but it will always have a non-empty boundary. Okay, so you can do that. You can deflate your manifold on those two skeletons, and you can compute this formula as the Euler characteristic of n, which will be okay. But now this gives the image of the generators. So there is a dimension of j to the m1, and they have to verify to fulfill M2. M2 condition. So you know that the dimension of the component inside the representation variety has dimension bigger than sorry, not 2. The dimension of G times M1 minus the dimension of G times M2. Yeah. The choice you have minus the relation you put. And I'm not claiming it's an equality, it's just a lower bound. And we almost have our relation. So here we see minus dimension of G times the Euler characteristics of N, but the one which appears in the Euler characteristic. And this is exactly this. Well, maybe I should, in order to write it exactly in the same way. It is exactly this formula when t equals 0. Okay, so this is a very general fact, and this bound when you do not take into account the term related to the tori is a very general bound given by this relation. Okay? So now how can you use the bound for a manifold with t-1 tori in order to prove the bound for a manifold with t tori? Well, you take M with t tori in its boundary. Let's say t equals 1, and you want to destruct this tori. So you can choose a loop, gamma, and drill your variety along gamma. We'll create a new element in the fundamental group, and here for the notation you have the generators of the fundamental group of the torus. So the idea from M, you construct a manifold with one less torus by drilling along a well-chosen gamma. Okay, so let's analyze the dimensions in this picture in order to understand what is a well-chosen gamma. What should we ask for gamma? So from N, drill along gamma. We will decide later on who is gamma. And you get a new manifold M prime with a new new fundamental group which is called gamma prime, which with there is a map from gamma to gamma prime, and and m prime has t minus 1 tori in its boundary, but it has the same number of boundary components as m. So I did not destroy some boundary component doing that. So if this procedure is good and I make my induction until there is no more tori in the boundary, there will still be the same number of boundary components, so the boundary will not be empty. So I will be able to apply the initialization. So this is just, we have to check that. We get a new manifold which has one less torus in the boundary, and you can compute that the new Euler characteristic is one less than the previous one. Okay, doing this procedure. Okay, moreover, sorry, I did. The wrong way here. M prime is included in M, so the fundamental group of M prime project to the fundamental group of M, and the kernel is exactly the normal group generated by the element I call delta, the meridian of the added angle. Okay, so now I had my distinguished representation, which was strongly irreducible and boundary regular. Okay. And now this representation can be promoted to a representation of gamma prime. Gamma prime to gamma, and the fact to note that this representation will still be strongly irreducible. In fact, strongly irreducible depends only on the whole image of the representation. Okay, and whether I see rho naught as a representation of gamma prime, the image does not change. So the irreducibility, strong irreducibility, does not change. So it is still strongly irreducible, and it is still boundary regular. Why is that? It's because in order for a representation of gamma prime to be boundary regular, I have to look at each torus in the boundary of M prime and check whether the representation restricted to this torus is regular or not. Okay, but now the tori in the boundary of M prime are in the boundary of M, I just destroy a torus, but the other one are the same. So the restriction of rho naught to a boundary tori of n prime is the same as the restriction of rho naught to the relevant boundary tori of n. So by assumption, the representation is regular for this torus. Okay. So now you can use the induction hypothesis. You have n prime with t minus 1 tori, and you have a representation that is strongly irreducible and boundary regular for the P1 of n prime, so you can use the induction hypothesis. So remark. You have a map from the representation of gamma to the representation of gamma prime, just the same one that we used, and let here I take a component at the right which contains the image of the component I was looking at, and this zero contains rho naught. So for this component of this representation variety, I can use the induction hypothesis. I have a bound for the dimension of V naught. What is my bound? So I look at here. I have t minus 1 tori. And I have the Euler characteristic of n prime. Okay, so let's write it in this way. I extract the desired bound for n, which is this one, and then I have to compute what lacks us, and in fact it is I have the default of n squared minus n. Okay, this is just using that this Euler characteristic is the one of n minus 1, so you get plus n squared minus 1 minus n minus 1 due to this t minus 1. Okay. And so what I would like to prove, gold, is that the codimension of my former component R naught inside this component is at the codimension most okay, if I prove that the codimension of R naught inside V naught is at most this term, then I will get the desired dimension of R naught. Okay. And okay, how may I compute this codimension? Well, I don't know very much about character varieties and dimension of character variety of three manifolds. So the only thing that I know is that Weil-Goldman formula, and so I will look at what happens on the boundary on this surface. How can I state this goal in terms of representation variety of this sigma 2? Okay. Maybe I would like to keep this picture. And so here I introduce, in fact, a very important tool in my work, I would say in representation of three manifolds, is that it's always a good idea to look at restriction to surface group, because you know a lot about surface group that you don't know about three manifold groups. So you have a map of restriction from which, well, if you have a representation of gamma prime, you can restrict it to this boundary component, any boundary component. So let's choose this one, which will be important for us. So I call it sigma 2, and okay. And now, what does that mean? That some representation from gamma prime is in fact a representation of gamma. What does that mean in this setting? It just means that you can feel the dreaming. So it just means that delta is identity. Okay, if a representation satisfies it goes to a representation of gamma. Okay. But this condition can be seen here. Okay, so so I will let X the component here containing the image of V0. So I always have to look at irreducible components. So I have a component here. I look at its image. It lies inside an irreducible component there. So I call it X. And S the set of representation of my surface group such that they map delta to 1. Now I say, I just rephrase this picture saying that R0 is the preimage under the restriction is a component of the preimage under the restriction of this subvariety. Okay? So if I want to understand the codimension of this one to this one, it would be a good idea to look at the codimension of S into X. But this is a problem about surface group. So this is not so hard. So we have a proposition here is that if we can manage, if we can choose this gamma such that rho zero restricted to this surface group is irreducible, if we can do that, then codimension of S inside X is actually equal to this n squared minus n, the same one as there. Okay, and plus this restriction will be a smooth point. Of both X and S. Okay. This restriction, of course, it comes from rho zero was already a representation of gamma, so it fulfills this condition. Of course, the delta is mapped to the identity. So the restriction of rho zero is a point in S, which lies inside X, and what I state here is that it is a smooth point in both varieties. And in fact, this is really easy to prove with Goldman proof, with Goldman dimension formula for dimension, because the irreducibility of rho zero gives you immediately. Maybe I will just prove this proposition and then stop explaining just what we will do the next time. So, in 2 minutes, the proof of this proposition is that first, the dimension at rho zero of X, well, it's a dimension at an irreducible representation of the representation space of the surface of genus 2. So it is exactly 3 2g minus 1 times the dimension of G, which is 3 n squared minus 1. Okay? And moreover, as rho is irreducible, it is a smooth point. So this part is not hard. And the other part, the fact is that we can actually compute the dimension of it. Okay, so what is a representation which lies inside S? But, well, if you are inside S, delta is vanished. So you have to look at the representation of A, B, and gamma. As delta is identity, the relation is that A and B commute. So A and B generates the Z2, and then you have a free product with gamma, which has no relation with A and B. So we have this one. And in order to construct such a representation, you have to choose a representation of the torus, and then to choose a representation here. So you can choose them independently, so the dimension add up. And here we have the boundary regularity of rho 0, rho 0. So we know that restricted to this Z2, this representation rho naught is regular. So we have, when we discussed the Goldman dimension formula for the torus, we already compute this. In this case, this is dimension of G plus the minimal centralizer dimension, which is rank of G. And then here you look at the representation of a cyclic group. This is dimension of G. Okay. And moreover, by the regularity, we know that this centralizer has the minimal dimension possible. So the dimension of the Zariski tangent space at rho 0 is the minimal possible. So this means that rho 0 is a smooth point. But anyway, let's forget about it. Now we have computed the dimension of X and the dimension of S, so we can just make the difference codimension of S inside X. So the difference is dimension of G minus the rank of G. N squared minus 1 minus N minus 1. So in fact we are almost done in the sense that, okay, there is a generic algebraic result that says that in this case, when you have a map, you have a point, okay, you have R naught in V naught, you have rho naught, and you look at the image, you can compute the codimension of the image, and the image of rho naught is a smooth point. With all this consideration, you know that the codimension at the beginning is less than the codimension at the end. So as we can compute the codimension in the surface group, we know that the codimension here is at most n squared minus. Okay, so with a general fact about codimension and pullback of submanifolds, subvariances, you have to be careful here, but it works in this setting. It only remains to find what? To find the gamma such that this assumption, the assumption in this proposition, is fulfilled, meaning the group generated by gamma and the torus group is irreducible. Okay, and this was already the case in Thurston and Culler-Shalen proof. You had to find gamma such that you make irreducible the representation of the torus. Okay. And I will briefly show this next time how to find it under the hypothesis on rho naught. Okay. And then I will move on related but different topics about still this restriction, how the restriction of representation to boundary components can give you information about the character variety. And I will introduce another tool, another important function, which is the volume of representations.
Questions?
How do you use a strong irreducibility instead of reducibility?
Because it's needed here.
Perfect.
Okay. If it's only irreducible, well, it's in fact there is something is that if you really want only irreducible representation, then you will have to ask more about the boundary regularity. Okay, there is. You can a bit weaken one of those assumptions, but you have to strengthen the other. There is kind of equilibrium to find.
Yes, but Thurston and Culler-Shalen didn't use it. Right?
They didn't use it, but it's in the case of SL2, the difference between strong irreducibility and irreducibility is very thin. So it's not clear. Well, in fact, in the case of SL2, they are almost the same, so it's not clear what should be the good generalization. Okay. In fact, as stated here, the Thurston and Culler-Shalen theorem is inside this one. It's really a generalization as stated here. Okay. Tomorrow I will find gamma with an additional assumption about irreducibility. I will, in fact, assume that rho is Zariski-dense because it's much easier to state. But there is always this interplay between both assumptions, the irreducibility kind assumption and the regularity kind. And if you are interested in a particular representation which is maybe not strongly irreducible or maybe not as a problem about regularity, you can try to play with that. But for a general result, I think this is the best equilibrium.